Hey, hi everyone, welcome to my YouTube channel and welcome to you this RAG playlist. So if you are following me on my YouTube channel, you guys may know that currently I'm running a RAG playlist where I'm teaching RAG end to end, starting from the very basics. Okay, I do have already one MLOps playlist also in my channel. If you want to watch my MLOps playlist, you can go to my channel and watch it. It may come in the I button also. You can watch it. So today we are going to discuss about chunking, which is very important topic in RAG that we need to understand. And I have prepared few HTML pages, and through some visuals I will explain you different chunking techniques and all, as well as we will do the implementation also in this session. Okay, so you can see what is chunking. The definition of chunking is already mentioned. So so chunking is the process of splitting large text documents or data into smaller segments before processing. So AI models, search engines and data pipelines can actually handle them. So chunking is nothing but just splitting large text or large documents into small segments. You can see there's one visual mentioned, big document.pdf, and this big document.pdf had 580,000 tokens. So if I click on this vast chunks, right, you can see multiple chunks are getting out from this big PDF. So it's kind of a visual understanding that I am trying to give meaning to you. You can see the definition: the act of dividing a large unit of information into smaller, semantically coherent pieces, each independently processable, indexable, and retrievable. So this is the whole and soul motto inside chunking. Okay, so before jumping into chunking or something more about chunking, we need to understand when chunking is not required. I have already mentioned, right? Chunking means splitting a big document in multiple pieces, right? And this is a technique which is used in the RAG or in general in any kind of data processing techniques, right? So even though it is very important topic to know, but we need to know when chunking is not required, because everywhere you do not need to use chunking. Okay, we need to understand when it is not needed, then we understand when we need it. So small atomic self-contained data, stream flow smooth, no breaking needed. When you have small atomic self-contained data, right, you don't have to do chunking. Here you can see I have showed one data flow, right? So you can see tiny.csv, short text, image.jpg, message 001, this kind of data, right? Which has only 8 tokens, 15 tokens, or maybe it has one event, one process. If you have this kind of data, you can see these are very small kind of data, right? It means you do not need to apply chunking on such data. That's what I am trying to show you through this visual. Below you can see I have mentioned these specifications like short conversations, a tweet, product review, or chat message already fits in one context window. Splitting destroys the coherence. So if you have some tweet or some product review or some chat messages, and these things will not be that big, which will not fit the context window of your LLM. What is the context window? Context window simply it means how much your LLM can read in one shot. This is the context window that we try to understand. And as you know, any tweet, any product review, any chat message mostly will not extend the or overflow the context window. Like you can see, loved the pizza. This is the input. Okay, and the token of this input is only 8, but the limit of any LLM is 128k token limit. But this input, love the pizza, this has only 8 token. That means you don't have to do chunking. Then something like atomic JSON records, a single user object or config entry. Each record is its own semantic unit. Splitting breaks the schema. So sometimes you may have a JSON record where your details have been mentioned. In such scenarios, if you really try to break it further, it will not keep its semantic schema or semantic meaning, right? Like you can see, you have a ID 42, name is Ali. So the total token for this JSON is 14. So this is very small token, right? That means you don't have to do chunking. Next is single image inference. Let's say one image to one VLM call. VLM is kind of a model that we use to process images. Okay, one caption. That means I am providing one image, and that image will be processed through one VLM. It is a model which can process image data, and by seeing the image, it will generate some caption, right? So the pixel grid is already at the atom, nothing to split. So that means if I provide one photo.jpg to my VLM, the mode of this process is single pass. It means you don't have to do chunking. Then the real-time event stream. Let's say IoT sensors, live thread, real-time logs. One event processed immediately, pre-chunked by nature. So what is happening here? Your IoT sensor is sending you real-time data. Okay, so in real time, it already chunked, pre-chunked. Why? Because when you are sending some data, right, you are sending real time. That means you are sending some messages at 9 a.m. Then you are sending some messages at 9:05 a.m. right? That means you are already sending the data in a chunk. So in such scenarios also, you don't have to do chunking. Then short classification, tiny in memory data sets. So these are the few cases where you do not need to do chunking. And now we need to know when chunking is essential. So without chunking, this fail: out of memory, context overflow, or terrible retrieval precision. So in few cases, your chunking is essential, or else you will have issues like out of memory, context overflow, or terrible retrieval precision. You can see you have a big data blob here, right? If I hover over it, you can see now this big data blob splitted into 3 chunks. As I've already mentioned, it's a big data. That's why you need to do split on it. So whenever I hover on it, it will split it. All right. Now, if your data is too large, what will happen if your data is too large? First of all, it will exceed the context window. 580K token novel versus 128K model limit. Impossible without chunking. So if you have a data where it has 580K token, then your 128K model limit will not help. You need to do chunking. Then RAM overflow. If you have a 52 GB of CSV file, loading it whole crashes in a machine. 10K row batches uses 240 MB peak. Okay. Then vector search precision. Embedding a 380 page PDF as one vector loses all specificity. Paragraph chunks equals to surgical retrieval. That means when you have a 380 page PDF, and if you really want to convert that into one vector, it will lose its specificity. That's why we need to do chunking. Then parallel processing. Chunking can be processed concurrently on multiple workers, multiplying throughput. So when you do the parallel processing, it will be more faster to process all of your chunk. Okay, so how the flow will go? You have a large document and you have 580K tokens. Okay, then what you do, you are using chunker, which will chunk your document or chunk your data, and it will chunk like 73 chunks. That means your 580K token document split into 73 chunks. Then these 73 chunks will be embedded separately, and then it will be indexed inside a vector DB. Now you can query and you can get your answers from your vector DB, right? What all things we can do by doing this chunking? We can build RAG over documents, we can do LLM book summarization, we can build massive ETL pipeline, we can do semantic corpus search, okay? We can do long audio transcription, code based understanding, and all we can do, okay? And below, I wanted to show you some live web playground, and I just wanted to show you how it happens visually. So here I have chosen a scenario, legal PDF. Okay, so your legal PDF is like our 380 page contract chunk at paragraph level for vector search. Each paragraph becomes a retrievable unit. Okay, so you can see right now this is the chunk size. The chunk size is 800. Okay, I have chosen the 800 as a chunk size 800 T means 800 tokens. You can see it's coming here. So when I have chosen 800 tokens, you can see it is divided into 8 chunks. Okay, 800 tokens, and total tokens are 6.4k. Okay, so you can see 8 chunks it has. First chunk is for parties, then second chunk is for term, then payment, then liability, then IP, then exit, then law, then dispute. So when I have chosen this 800 token, you can see it has divided each part very precisely, and you can see also in the graph, see, this is for parties, this is for term, this is for payment, this is for liability, this is for IP. So based on the color of this text, right, you can see the graph is flowing here. Okay, so now if I really want to change it, let's say I am just making it 400 medium, let's say 200 chunk, 200 token. Okay, so when I have did it 200, now you can see it has 13 chunks. Because why? Because I have reduced the tokens, and because of that, see, now it is more chunks. This is 13 chunks, and 13 chunks are now split into multiple parts, and you can see the repeated parts also, because you have done some less amount of token chunking, and because of that you can see more repeated part, like parties is coming here, then term is coming here, payment, liability, IP, exit, law, dispute, again you can see parties coming here, term coming here. So because of the chunking, right, this chunking chunks are getting changed. Okay, so you can see also more this graph you can see here. You can, if you make it low, very tiny, like 50, then you will see more graph like this. Why? Because now we will have more chunks, like 18 chunks now you have. Okay, so this is how it works. Now when I choose chat message, so for chat message you don't have to do chunking, I have already mentioned. So for that you can see it has a normal flow. Then code repo. So when you have code repo, on that time also you have to do chunking, because you need to do chunking, as your code may have a very I would say your code may have lot many numbers of code, and maybe because of that you need to handle it. You can see I have chosen a very 50, again same thing, it is divided into 18 to chunks, and as per that you can see it has login, logout, query, connect, handler, parse, user, session, login, logout. So what it is doing, it's trying to fetch specific part from your code and trying to chunk it, and each chunk has a 50 token limit, right? But if you try to speed it up and try to make it huge, right, now you can see for 800 tokens here you have 8 chunk, and for the C you have proper chunking. Now you have proper login part covered, you have proper logout part covered, and other parts are covered. Now here you are not repeating any part of your code, right? So choosing a proper chunk size is very important, and that's what I wanted to show you through this visual. Then for reviews also you don't have to do it. Then for news, again for news you have to do it, because same logic, the way I have mentioned for legal PDF and code repo, same logic for news. All right, okay, now we talk about the chunking strategies. So we have understood that how chunking works and when to use chunking, when not to use chunking, but now we need to know about chunking. Okay, and after this implementation I will show you the practical. So I will discuss 8 real strategies with proper documents. Watch each technique split text step by step. So right now you can see I have a file transformers nodes.txt, and it has this simple plain text. The transformer architecture revolutionized NLP by introducing self-attention mechanism. Each token attends to all other in parallel, capturing long-range dependencies without recurrence. Models like GPT and BOT are built entirely on this foundation. So we have a txt file like this, and it is a plain text. And the very first technique that we are going to discuss, that is the fixed size chunking. What is this chunking is all about? So splits any text into equal size windows of n tokens regardless of sentence or word boundaries. Optional tight overlap reduces boundary information loss. Zero linguistic intelligence, purely positional. What it means, let's see in practical. You can see I have a step 1, full text as a raw token stream. So what I did, I just copied this full text and kept it here. Okay. So you can see it has 7 tokens, and I am not applying any boundaries. Okay, so I just click on this next step. See, now what happened? In step 2, what happened? I applied chunk size 10 and I am doing no overlapping. Overlapping means when it will chunk, first chunk will be there, and when next chunk will come, so few part of the first chunk will come into the next chunk. But I am choosing no overlap. It means that none of the part of the first chunk will come to the next chunk. As simple as that. Okay. So you can see now what it has done, as I have chosen 10 as a chunk size, so from starting from the till the this dot, it kept it as a one chunk. Then you can see cut is coming. That means the first chunk will be till this much, from the till this dot, then from each till the capturing. Okay, this will be the second chunk, then again cut, then from long range till this bird is coming as a third chunk, then from R till this dot coming as a fourth chunk. As you can see that as I have chosen chunk size as 10 and there are no boundaries in it, right? That's why you can see sometimes it is trying to capture some irrelevant information. How come? See, this chunk is fine, it's coming starting from the and coming to this point or full stop, but for the second chunk you can see it is trying to capture from each until the capturing. That means it is trying to capture half of the sentence, it is not capturing the full sentence, right? Because it is not actually trying to understand anything semantically, it's just trying to do simple split based on the chunk size. Okay, so you can see this is the chunk 1, this is the chunk 2, this is the chunk 3, this is the chunk 4. So chunk 1 has 10 tokens, chunk 2b has 10 tokens, chunk 3 also has 10 tokens, but at the end we had very less text left, that's why we have 7 tokens. Okay, so now if I click on next, you can see the output. What I did, now I added overlap 3. I added overlap 3 here, you can see. As I added overlap 3 here, what happened? You can see first split came from the till the mechanism. Second chunk, see, second chunk started from self attention till other cell. Now you can see self attention in the first chunk also. Can you see that? See, self attention is already in the first chunk. As I have added overlap 3, that's why it is trying to take some of the part of its previous chunk. That's it, starting from self attention till orders in. Then you can see in the chunk 3, see, all orders in is starting from here. It is again taking some of the part from the previous chunk. So like this it is coming. Okay, great. So this is the all about fixed size chunking. And if you really need to know about its pros and cons, you can see it mentioned here. Again, it is extremely fast. Its time complexity of this thing is order of n. Simply it means that it's not doing anything else, it's just splitting it randomly as per your chunk size. So it is fast. No models or parsers needed. Deterministic and reproducible. Words on any byte stream. So you can use it in any byte stream, no issues. But it has a lot many serious cons. First of all, cuts mid sentence and mid word. You have already seen, right? It's cutting mid sentence, mid word, and that may cause some issues when we add this into our rack project, right? Then no semantic understanding. There's no semantic understanding. It is just randomly cutting as per my chunk size, right? Overlap waste storage space. So if you add overlapping here, right, sometimes it may eat more storage that you expect, right? Then terrible for prose retrieval. Okay, so that's why fixed size chunking mostly we do not use it, but these are the scenarios that I wanted to mention. You can see the performance, speed is good, there is no cost for it, no setup you need to do for this, but the coherence is poor for this. Okay, next is the recursive. What is the recursive chunking? So for recursive chunking we have a multi-paragraph prose. Okay, so we have a gradient descent.txt file, and we have this basic text about gradient descent, and you can see it is in different lines with some lines also in our text. Okay, so what is recursive chunking? So recursive chunking is, it tries separators in priority order, slash and slash n, then sentences, then spaces, then characters, falls back to the next level only when a block exceeds max size, produces natural text hour chunk. So how this recursive chunking works, it tries to split recursively. First it tries to split based on this double slash n, the backslash and backslash n. Simply it means it tries to split it based on the paragraph. After the paragraph, it will try to split based on the sentences. After that, it tries to split based on the spaces. And after that, it tries to break or split based on the characters. Okay. This is how it works recursively. That's how we call it as recursive chunking. And how it works, let's see in the example. You can see I have a full article, 3 paragraphs separated by backslash and backslash n. So you can see the whole text, right? And this is the paragraph break. So this is the paragraph break. Okay. Now let's do the next step. See what happened. Split on backslash and backslash n. Then 3 paragraph blocks. Paragraph 2 greater than max size was split on dot. What happened? So what we did, it has first splitted based on backslash and backslash n. Okay, that's why it is the first chunk, right? You can see till steepest descent, and you can see this is the steepest descent that we had. Okay, first sentence or first paragraph, then chunk 2, then it got this one. Okay, then it took this one, chunk 3 took this one, then chunk 4 took the rest of the one. So how it did? Simple. It splitted based on backslash n and backslash n, and that way it got 3 paragraph blocks. And since it has got 2 paragraphs which is greater than the maximum size that we gave, that's why it has again splitted based on the sentences or the dot or the full stop, whatever you say. You can see right here, I have already mentioned. It tries to split first based on the paragraph, then it will split based on the sentence or the full stop. So it has splitted based on the new line, okay, backslash and backslash n, okay, and it got 3 paragraph blocks, okay, but it got only 2 paragraphs after doing that. That's why it again splitted based on the dot, and that is why we got this 4 chunks. Okay, and final chunks with 8 token sentence overlap at boundaries. So when we added some sentence overlap, we got this 4 chunk, where you can see in the second chunk this the direction till the steepest descent already copied from the previous chunk. Likewise in chunk 3 multiplied by the learning rate copied from the chunk 2. Same wise, how large each step is copied from the previous chunk. So when we added the overlapping, it has overlapped its chunk, right? Okay. Now again let's try to understand its pros and cons. It respects the sentence and paragraph. So here it is respecting the sentences and the paragraph because it is trying to do it through some separators like paragraph, sentence, space, characters, right? Then no ML model needed. Here we are not using any kind of machine learning, right? Then configurable separator chain. If we want, we can create or provide our own separator chain also, when that we see when we do the practical, but you can provide your own separators also if you want. Then merge better covariance than fixed. Again you can see here, right, this is much better than fixed because here it is at least respecting the paragraph, sentences and all, right? But it has some cons too. Its fixed separators miss domain logic, as these are very fixed separators, right? So in your domain or in your data it may have some other logic. So in such cases this way it will not work. You may have to change the separator or may have to do something else so that it can work. No topic awareness. So here it is not doing anything based on the topic. is doing simple based on the paragraph, based on the sentence, right? It is not really understanding any topic. Then manual overlap tuning needed. So overlapping is also a issue here. You have to obviously maintain and check before choosing any overlapping number in your case. Then fails on separator less text. So if your data or if your text doesn't have any separators, then this way will not help anyways, right? So these are the issues of this case. Okay, all right. So now let's talk about document based chunking. So for document based chunking, what do we have? We have a separate data set. We have a .md file where we have what is a neuron, what is activation function, and we have a Python code of a ReLU function, okay, and some data. So we will understand about document based chunking on this data set, okay. So what is document based chunking? So document based chunking uses the document's own markup as chunk boundaries, markdown headings like this single slash, not slash, single hashtag, double hashtag, triple hashtag, like you can see in this data, right? It has single hashtag, double hashtag, triple hashtag, right? It tries to understand using these markdown headings, HTML tags, PDF section headers, or code or function signatures. Each chunk goes to one logical section, fully self-contained. So now let's understand. So this is the step 1, markdown document with visible structure markers. So this is the data that I am already showing here. I have pasted it here. Okay. So if I click on the play next step, can you see something? It has splitted at every double hashtag heading, then 4 logical section extracted. When it did this 2 hashtag heading split, it got one part for what is a neuron, it got one part for activation function plus ReLU formula, then it got another part called training process. So you can see you have this kind of document, and through this document based chunking you can easily chunk your data logically by just following this markdown headings. Okay, if I click on the next step, you can see H1 title prepended to each chunk as context prefix. So that's why you can see now how it is coming. Introduction to neural network. What is a neuron? It's coming like this. Then introduction to neural network activation functions plus ReLU coming like this, and then introduction to neural network, then training process coming like this. So this is the example of document based chunking. Again, what is the pros and cons? You can see here. Perfect logical boundaries, each chunk self-contained, headings injected for context, preserves code, list and tables. But it has some cons also. It requires structured document. Again, if you really want to implement document based chunking, you need to have structured document. Then oversized section not split, fails in unstructured rows. If you have unstructured data, this way will not help. Okay. Then next is semantic chunking. What is semantic chunking? Let's understand that. So for semantic chunking also we have a data of txt file, mixed topic paper.txt file. So what is the semantic chunking? So encodes each sentence with a dense embedding model. What it does, it encodes each sentence with a dense embedding model, computes the cosine similarity between the adjacent sentence pairs. Wherever similarity drops sharply below the threshold, a chunk boundary is inserted. Boundaries follow meaning, not position. So what it does is simply calculate the cosine similarity, and based on the threshold it decides when to chunk. And because we are using embedding model here, an embedding model preserves the semantic meaning, and that's why this is called as semantic chunking. So let's talk about it, how it works. So I have a data, and I have splitted this data into sentences, compute embedding similarity scores. So this is the first data. Convolutional neural network excel at image classification, achieving 98.6% accuracy on CFIR 10, and the similarity of that is 0.01. Then ResNet introduced residual skip connection, and this got similarity 0.87. Then next text got the similarity 0.24. So here you can see the drop. Here you can see the drop of the similarity. Then you can see the economic something is there. This is 0.89, which is increasing. Then for the next loss we got similarity like 0.85, right? So here I have chosen the similarity threshold 0.5. So if your similarity threshold is not greater than this threshold, then that means we cannot keep that chunk with others. Okay, so that's why you can see we kept these chunks together and we kept these chunks together. These are separate because these are the separate topics altogether that is discussed. Okay, so if I click on this play next step, you can see it. See what it did, it checked that similarity 0.24 is lesser than threshold 0.50. So breakpoint is S3 to S4. So and it has seen that this part is lesser than the given threshold, that's why it has splitted this part and it has splitted this part. Okay, and at the end we got this two kind of chunk. So one chunk is talking about completely computer vision, another chunk is talking about its economics or the AI impact. So what it is doing, it is semantically trying to understand that when you have a text document, it's semantically trying to understand this above part was discussing about completely computer vision and the another part was discussing about its economics or the AI impact. Now this way when you fit this data into the LLM, it will be better for it to understand that okay, this chunk is all about computer vision. If someone is asking any question related to computer vision, it will pick this chunk, not this chunk. Or if someone is asking about anything on economics, about AI or something, it will pick this chunk. So it will be easier for the AI to respond back, right? And it has some pros and cons. Again, we need to know. It detects a real topic boundaries, which is a very good thing. No manual rules required. Large language model ever. So at the end, we are using embedding models here. So models are required. Adaptive chunk sizing. So here chunk size are pretty adaptive. Based on your data, it will change its chunk size. But it has some cons too. Like embedding model required, you need an embedding model here. It's slower. If you have a bigger data, it will be slower. Then threshold need calibration. Like we chose 0.5 as a threshold for this work. But for other project, you may have to choose some other kind of threshold. So it really depends on that part. Then very long docs are expensive. So if you have a very long document, then applying embedding on top of them will cost you a lot for sure. So these are the pros and cons of semantic chunking. Then LLM based chunking. What is that thing? So sends the full documents to an LLM with an explicit chunking prompt. The model applies legal, medical or domain reasoning to propose chunk boundaries, understanding narrative intent and clause structure, not just position. So for this we have a data like license agreement data. That is what we are going to use in this chunking technique. So LLM based chunking is simple. Just send a prompt that you need to chunk based on this logic or based on this kind of domain, and it will do its job. So you can see we are saying we are giving a system prompt to LLM that split this contract into standalone legal clauses. Each chunk must be a complete provision, written boundaries with reasoning. Okay. So when we provided that, so you can see it has already tries to separate these three parts. If I click on this play next up, you can see it. So what LLM saw, three clauses found. Boundary 1, after business purposes, rights grant ends. Boundary 2, after monthly interest, payment obligation ends. So by seeing this whole data, it has found out this is the boundary. Okay, then this is the boundary. So all are highlighted in different color for your understanding. So it got this kind of parts as a boundary, and if I click on the next step, now it has got your chunk. So as per the LLM, this part discussed about the rights grant, this part discussed about payment obligation, this part discussed about termination procedure. So what it has done, it has tried to understand the intent or the meaning of the legal contract, and as per that it has chunked the document, and I guess it is pretty good. Okay, but it also has its own pros and cons. Again, understands legal and domain logic has to be there. So you need to use some LLM model which will have the idea of the legal logic or legal domain logic. Then provides boundary reasoning, handles ambiguous structure. So sometimes we may not be able to choose proper chunk size, but LLM is able to do it. Then generates chunk summaries. It's generating chunk summaries too for your understanding, but it is expensive. This is the cons, because you are sending the whole document to the LLM, right? So it will cost you some API calls, so it is expensive. Slow inference time, because LLM will take some time to process it, so it will take some time. Non-deterministic output, because LLMs are black box model, so outputs will be not deterministic. Then needs prompt engineering. You need to add a prompt engineering to do this whole stuff, because you need to create a chain, you need to add the prompt with that, you need to add the LLM with that, and also so more things. That's why it needs a prompt engineering. Okay. Next part is the agentic chunking. What it does? So an LLM agent comes into the agentic chunking, reads the document sequentially, maintaining a proposition buffer. After each section, it decides extend current chunk or seal it and start fresh. Generate a dense proposition summary per chunk for precision retrieval. So for the agentic chunking, we are using this patient cardiology.txt file. Okay, let's see it in live. Okay, to understand it. So what is the step one? Agent reads cheap complaint form proposition chunk open. So this is the proposition: 56 million acute chest pain, 8 by 10 left arm radiation, and diaphoresis 2 hour onset. Okay, so this is the data. So agent reads the first section, builds the proposition, patient, and this. So this is the proposition that it has built. Now agent checks, is this a complete clinical unit? Yes, seal it. So if this part is a complete clinical unit, then it will seal it. That means it will be a chunk one. See, so what it has done, it has created multiple propositions by seeing the data. So first proposition already I have read. This is the second proposition, which is all about history and examination. This proposition was on this. You can read this out here. I'm not reading it out here. So here you can see we have this two kind of proposition, and based on that it has chunked. Okay, so at the end it has done the assessment. After the assessment and the full proposition, it got this 4 chunk. So each chunk has its own proposition, and based on this own propositions, this agent has divided the data in multiple chunks. So I believe this is also a good way of doing the chunking, and it has also some pros and cons that you can read it out here. I am not reading it again. I just want to show you. Then late chunking or the post chunking. What is that thing? So what we do here, we embed the entire document first. Whatever document or whatever data you have, you embed it first using a long context encoder. Every token embedding attends to all other tokens before any splitting work occurs. Then pull the globally ever embedding into chunk. He and the physicist already encode equals to Einstein if chunking. Okay. Again, about this post chunking or late chunking, we will deep dive when we do the practical. But simply you need to understand, in this case, at the very first time, we directly send our entire document. Okay. Okay. This is how we do for late or post chunking. So for late or post chunking, I will discuss later when I show you the practical part. In the practical part, we'll deep dive more through some animations. I will explain it to you how this late chunking works. Okay. The last part is hierarchical chunking. So for the hierarchical chunking, we have some data also, some MD file where we have multiple chapters, and each chapter has its own sub chapters, right? So that we understand the hierarchy chunking. So what hierarchical chunking? So it builds a multi-reason tree. So in hierarchical chunking, we create a tree, and this tree will have multiple levels. You can see coarse L1 parent chunk like chapters in this case, then link to fine L2 child chunk like subsections. Retrieval fetches the precise child for exact answer, then walks up to the parent for surrounding context. So what happens whenever it tries to fetch the data, right? It first try to check through the child chunks. Okay, if it is able to get the answer through the child chunk, it will be okay. If it is not able to find the answer from the child chunk, it tries to go to the parent chunk and try to find the answer. So what it does is trying to do it through some multiple labels. First it will go to the L2 or the child chunk, where it will try to understand, okay, whatever user asked, do I have the answer in the child chunk? If yes, it's good. If it is not, then it will go one level up, L1, where parent chunks are there, and through that it tries to find out the answer. Okay, so this is the hierarchical way it will do. Again, when you do the practical, you will find it far better way. Okay, so here you can see I have this chapter 1, chapter 2, chapter 3. Okay, and it has L1 parent 1, it has L1 parent 2, it has L1 parent 3. So when I click on the next step, can you see? So for the L1 parent, chapter 1 installation, this is the L2 child. So for this parent, this is the child label. Okay, and this is the child label for this part. Again, for this chapter 2 configuration, this is the parent label. And for this parent chunk, these are the child chunks. Again, this is the another parent level troubleshooting, and for this we have this two child chunk. So that's how it will do it. And when query hits, what it will do, like if I ask this question, how to set API key, what it will do, it will hit the L2 child. Okay, because this answer is already there in the L2 child, so it will directly hit the L2 child and get the chunk. But if the user asks anything related to this configuration, right, so what it will do, it will automatically fetch from L1 parent, because L1 parent has that information. That's why it will go that there and it will try to answer. And again, hierarchical chunking also has its own pros and cons, like precision plus context in one call, multi-resolution retrieval, parent summarizes at scope, scales to huge documents. It has a good use case, but it has some issues like complex tree to build and store, because it will have multiple levels, so it is a bit complex to store. Higher storage overhead, because it will have multiple levels, each level will have multiple chunks, that's why it requires more storage for you to store. The retrieval logic more complex, because it will have multiple levels, so here you need to write proper retrieval logic for these, which is not very easy to do. Then overkill for small docs. If you have a small documents, you do not have to use hierarchical chunking, because it is only useful when you have big documents, when you have multiple hierarchies or multiple sections, subsections in your document. Such cases, I guess, hierarchical chunking will help you out. So this is the part that I wanted to discuss about chunking strategies. Then now what we do, we go to the VS Code and we try to implement our chunking techniques, so that you will get it far more better way. Okay, so now we focus on the practical part of our chunking technique. So you can see I have opened my VS Code, and inside my VS Code I have prepared this notebook. So you can come and you can download this notebook from the video description, and you can reuse it if you want to. Okay, so this notebook has everything properly commented. Okay, so that you can implement it directly by just seeing the notebook. Okay, so before starting, I do have one .env file, and in .env file I have kept two API keys. One is grok API key, another one is Gina API key. What is Gina API key we discuss later, but for now grok API key is something that we need to focus on. So what is grok? So grok is nothing but it is an inference platform where you can inference different LLMs. Okay, and for free you can do it. So how you can do it? I will just go to my Edge and search grok API key. If I Google grok API key, right, you can come in this section, API key is grok cloud. You can click on this. Then you have to log in using your GitHub account or Google account, and then you can copy the API keys directly from here, and you can keep it inside the VS Code. Okay, so that's all you need to do while building this whole setup. Okay, so now the thing is, if you focus in my notebook, I have kept that grok API key here. So what is the grok API key? This grok API key is nothing but this API key will help you to inference different LLMs. Okay, and it will be much faster. That's why we are focusing on that. Okay, so okay, great. So now let's do few installation. Here you can see I have done some installation of some libraries: LangChain Community, LangChain TextPeter, LangChain Olama and all, LangChain Grok, LangChain Experimental and all, so on. I have downloaded some analytical libraries also that we need to use it in our project. That is why I am doing that. Okay, so I'll just quickly execute this code. So this code will now install everything in my environment. You can choose the environment from this page. You can come here and choose your environment. So right now I have chosen my own system Python environment. If you want, you can create your own virtual environment and then you can connect with this if you want. Okay, but for now I am trying to show you through the direct notebook implementation, and that's why we are doing this way. Okay, so you can see it is showing all dependencies installed. It means my all dependencies are installed perfectly fine. Okay, now let's go to the next code. Okay, so here what I have done simple loading my .env file using a load.env, and then I'm setting up my grok API key. So I have my grok API key inside my .env file. So you can use this grok API key directly to connect with your grok. Okay, so now I have prepared few corpus AI. You can see corpus AI is there. Then you can see corpus ML is there, right? So what is corpus AI, corpus ML? So corpus AI and corpus ML contain some text data about AI, and this corpus ML contains some information about ML. So this is the data that we are going to use in our chunking. Okay, so these are the data which we will be using in our further codes. Okay, so if I execute this code, you will see my corpus AI has 3276 characters and corpus ML has 2275 characters. Okay, so this is the size of my data, and you can see one function I have written, inspect chunk. What this function will do, again I am not going to explain this function to you. You can come and check the notebook and you can understand it. But this notebook is nothing but this notebook you can use to inspect your chunks. So once chunks will be created, right, then just to beautify it in a prettier manner, that what is the total chunk, then average size of the chunk, minimum and maximum number of chunks, and so on, just to show this kind of metadata, I have just created this function. Okay, so this is what this function is doing. Okay, so I'm just executing this code. You can see it's coming like inspector ready. It means my inspector function is ready. So now we focus on fixed size chunking. Okay, we focus on fixed size chunking, and you can see the core idea again. Same discussed already, right, in that HTML page that I have showed before. Again, same thing mentioned here. Core idea is split text into equally sized pieces measured in tokens, not characters. So here we split the text into equal sized pieces measured in tokens. So based on token size, we are going to split it, not based on the characters. Okay, and it has mentioned the pros and cons that you can read it out. So I'll directly come to the implementation part. Okay, so what I do, I create a new cell and I'll try to execute this code so that I can explain it to you. Okay, first of all, I am going to paste the libraries. Okay, this TikTok token. Okay, then your LangChain text splitter and all. I have simply pasted it here. Okay, so next part is the splitting part, right? So what I am doing here, I am creating one variable talk splitter, then I am calling the token text splitter, and I have provided the encoding name as CL100K base. Chunk size I have given 200. Chunk overlap I have given 20. Okay, that means 200 tokens per chunk. So each chunk will have 200 tokens, and out of that 20 will be overlapping. Overlapping means what? Few of the parts, that means 20 token will be copied from the previous chunk. Okay, that's what simply it means, the overlapping here. Okay, I will show you to the example so that you get it. So I am applying this on top of the corpus AI data. Okay, so if I execute this code, you will see the chunk. So if I call chunks uh, chunks okay, you can see the chunk, right? So I'll just pick the first chunk. Okay, I'll fix the first chunk and I just simply paste it here so that we can see it. I'll do the toggle word wrap so that we can see it. So this is the first chunk that it has extracted from the corpus AI data. So this chunk has 200 tokens. Okay, then now if I try to copy paste this second chunk, okay, if I try to copy paste the second chunk, this is simple, we can do using indexing, right? So if I really again paste it and do the word wrap, you will see few part copied from the previous chunk. Like if I mention legal becomes legal documents in second, right? See, it is copying from here, so you can see the same part is already there in the previous chunk. Legal document in seconds, work that previously consumed 360,000 man hours per day, black. This was the ending of the first chunk. Now as we have given the overlap as 20 tokens, that is why it has taken it from here. See, legal document in seconds, work that previously consumed 360,000 man hours per year, BlackRock's Aladdin system manages, and blah blah blah. So this is the overlapping feature I wanted to show you. So it is trying to overlap 20 tokens from its previous chunk. Okay. So this is the chunk that you can see here, right? So now if I just call this inspect chunks that I created before, right? I just delete this part because we don't need it anymore. And if I really execute this code, you will see the summarization. So we got total 4 chunks after doing this splitting, and average size of the each chunk is 898 characters, and minimum chunk size is 440 characters, and maximum size is 1110 characters. Okay, so this is my chunk, and you can see chunk 1, chunk 2, chunk 3. Okay, great. So the next part is, you can see, let me again copy and paste it in the above so that you get it. Okay, so this part is about character text splitter from tick token encoder. But how is that different than the token text splitter that we just used? Again, this is comes under the fixed size chunky. Okay, but how is that different? Before explaining you through the code, I am going to explain it through the example that I have written above. Okay, you can see when you have a data, when you split based using token text splitter, it splits based on number of tokens. Now one token does not equal to one character. So if I Google one token, hold on, if I Google one token equals, one token is how many words? If I search this, you will get the answer. See, one token approximately 0.75 words. So one token is approximately 0.75 words in English. This means for every token you can expect it to represent about 3/4 of a word on average. So one token doesn't mean one character or something. It means 0.75 words. Okay. So that is why when we use token text splitter, we split it based on 5 tokens. Like here in the example I have shown to you, chunk size equals to 5 tokens. So when it did this splitting, it got it like this. ChatGPT is a then powerful AI system, then that understands and generates human like text. So this is the split based on 5 tokens, not 5 characters. But when we use character text splitter, on that time it does it based on the characters. So when we provide the chunk size is 30, when we use the character text splitter, on that time it works based on the character, not based on the token. So now chunk size 30 means 30 character approximately. Okay, we are talking about character now. That means it has 30 characters. So you can see because of that we got less amount of chunks, and because of that you can see we are getting a bit complete sentence. For this we are getting half complete sentence, but for this we are getting full complete sentence. Not exactly full, but at least better than the above. Like ChatGPT is a powerful AI system that understands and generates human like text. So each chunk is split based on character length. Okay, you can see each chunk split into based on character length. Then tokenizer is only used to estimate size, not enforce it. Churn looks more natural because we are doing character by splitting, right? So this is the use case, and this is the same I have implemented below using character text splitter. Same thing I have provided. I have just used character text splitter, nothing else. And if I execute this code, you can see when I implemented same on the corpus AI, I got this data. I got 6 chunk. Each chunk average size is 554 characters, and minimum 352, maximum is 733 characters. Okay, because we chose chunk size as 150 here, and I have chosen chunk size like 15 as a overlapping chunk. So because of that we got something like this. Okay, all right. So next we talk about Yeah. So next we talk about recursive chunking. So I have already explained to you how recursive chunking works. What it does, simply it tries to split or separate based on multiple separators. Like first it will try to do using backslash and after that it will try to split based on backslash and then it will try to do based on this full stop, then based on space, then based on something else, right? So try progressively smaller separators, paragraph, sentence, word, character. Recursively fallback until chunks fit. Langcha's recommended default. So when we provide the chunk size, whatever chunk size we provide, so until and unless it is able to match the chunk size, it keep on splitting based on this separator given, like paragraph, sentence, word, and so on. Okay. And the fun part is you can edit the separators also. So as I have mentioned already in the HTML part, I told you that in your case there could be some domain specific separators, right? So such cases you can add your own separators while implementing it, which is quite dynamic based on the use case, right? So let's see that same thing in the practical first. Again, I'm going to copy paste this above so that I can explain it to you separately. Again, I'm doing simple thing. I'm simply importing the LangChain text splitter, recursive character text splitter I'm implementing, and here what I'm passing the chunk size. Chunk size is 512 here. Okay, then chunk overlap is 64 here. And now here I am passing the separators. You can see I am manually mentioning all the separators that already mentioned in the LangChain documentation. But if you want, you can change these separators. You can give your own separators if you want to, based on your domain, which is very good as per your use case. Length size is length. That means it will do based on the length of your characters. Okay. Keep separators equals to false. So when I do this chunk and execute this code, now again, I am not going to show the chunks anymore because it does not make sense showing you the same thing. It will do the chunking only. So through the inspect chunks, we can see the more detailed information about it. Okay. All right. So now what recursive text method did. So we got total 10 chunks. Okay, and the average size of each chunks is 326 characters, and then min max we got 88 minimum character length, and 471 is the maximum character length. Okay, so we got 10 chunks by doing this splitting. But recursive character text splitter provides you further more things that you can implement, and that we discuss. Okay, so I am copying two more methods. I am copying two more methods below. So the first method is if you really want to do small chunks, okay, and small chunks we choose when we have a QA kind of data, when you have a QA data, right, question and answer data. On such cases, giving small chunk size is actually makes sense because we will not have much data, so you can divide it into smaller chunks. Again, I do not have any QA query for now. I am applying that on the purpose AI. Okay, and if you have a large document, if you want to work on the summarization part of any document, right, so such cases giving bigger size chunk makes more sense. And if I really show you, you can see. So when I have chosen smaller chunk size, I got 19 chunks, and when I chose bigger chunk size, I got 3 chunks, which is completely expected, right? Great. Other than that, there are another thing that we need to know, that is this one. Let me again paste it. Regex sentence boundary separator. As I've already mentioned that you can put your own separators as per your use case. So you can put a regular expression also in your separator. So you can see I have given backslash and then backslash and then I have given this regex thing. What is it? What this regex is meaning? This is meaning the sentence end. Okay, this is what it is meaning the sentence ever split. So once one sentence ends, it will split based on that. So this regular expression is trying to express that. So again, this is just for your example. If you want, you can put your own regular expression as per your use case, which is what I wanted to show you mainly here. And others parameters are okay. And there's another thing you need to pass, is separated regex equals to true. Because you want to split it based on the regular expression that you have provided, you have to provide this is separator regex equals to true, so that it can do the splitting based on the regularization parameter 2. Okay, great. Again, if you see the chunk, you can see that I got 12 chunk roughly here. Got it? All right. So now this is one simple example. This is nothing but this is one simple example that I wanted to show you. What this example is telling. So this is split documents. Okay. There's another thing called split documents. So when you have a text splitter like this, right? And and in general, when you read any data using LangChain, okay, that we do it in the retrieval section. After this video it will come up. So when in general you try to um, read any data using LangChain, you will get a document like this. If I show you the source docs, you get data like this. Okay, so this will contain a list of documents, list of LangChain documents to be specific. This document class comes from LangChain, and if I just paste it here and try to toggle the word wrap, and I can show you like this. So in general you will get data like this when you try to read any data from any document using LangChain libraries. In our case we are not reading any data using LangChain, that's why we are not getting this way. But when in future when we do it, you get a document like this where you will get a metadata. So in the metadata it will contain the source, then the author, then the year, and in the page content will contain the actual text or the actual data, like here I am showing it to you, right? So this is the page content will contain actual data, and metadata will be the data of your document. That okay, what is the source of the document, what is who is the author, who is the what is the year. So this kind of metadata you will get, right? So when you do chunking on this kind of data, okay, you have to use something called split documents. So again, array std I already got it from here. If I show you, I already got it from here where I have already called the recursive character text splitter, right? So when I call the recursive character text splitter, I call the split documents. Okay, when I call the split documents, then I am providing the source docs. So whenever you get a data in a document format, which you get mostly, okay, so in such cases you have to use split documents, not split text, because we are directly sending the text in our examples. That's why I was using split text. But when you get a document like this, which you always get when you read it through LangChain, you have to call split documents and send the source document, okay, and then it will apply the chunking same way. And if I really want to see that, see again when I did the inspect chunk, I got the details that by calling the split documents, I got 10 chunks where average size of each chunk is 326 characters and minimum 88 is the characters number and maximum is 471. Okay, so this is the thing that I wanted to mention. Great. All right. So this is all I had for you for recursive character text splitter. So another thing that I wanted to mention, that is called create document. So as I have already mentioned, right, whenever you read any document using LangChain, you will get it like this way only: document, metadata, page content. But if you want to create your own document manually, you can do that too. For that you need to add the metadata, like I have added one metadata, okay, in a list of dictionary. Okay, then what I am doing, I am calling this reg std, then I am saying dot create documents. Then I am sending up the corpus here, I am sending up the data directly, and then I am passing the metadata. Okay, but if I execute this code, you can see I got this data, and if I call the rec created, you will get the data. See, I am getting 10 chunks, right? And each, because I have used create documents, so I got chunks in this document format, which will be like this in real cases too. So if I show you the first document, it will be coming up like this. So if I really copy it and paste it below, and I do toggle word wrap, see, you will get it like this. This is the first document which has this metadata. So metadata will be same for all the data because this is the same txt file we are referring to, right? Then this is the page content. So this page content will contain the chunk, right? So this is how you can call the create document and you can do the chunking this way. Okay, so this is all we have for our recursive character text splitter. I hope you have understood recursive character text splitter very properly, right? All right. So now what I do, I just delete this part because I have kept this code in one page anyway, so no point behind keeping the whole thing. Yeah. So if you execute this code right, you will get all the details here one by one. Okay. So you are good with recursive character text splitter, recursive chunking. The next thing that we discuss, that is document based chunking. Okay, now we understand about document based chunking. So again, I have discussed about document based chunking in the HTML part, but here you can get the idea. So exploit native document structure, headers, sections, pages, paragraphs, as these split boundaries instead of arbitrary character counts. Header paths become searchable metadata. So when you have a document which has some structure, on such cases, document based chunking makes more sense. And in our case, we have one data. So if you can recall, we had corpus ML, we had corpus ML. I'll show you that. Yeah, so we have this corpus ML data, which has this kind of structure. You can see this hashtag, machine learning fundamentals, and so on. So it has headers. Okay, so we are going to do this splitting based on that. This is called document based chunking. So in LangChain, there are multiple ways, multiple options that you can do to do uh, document based chunking. So first we talk about the markdown header text splitter. What is the markdown header text splitter? It's nothing but it will be used when you have a data or a document which is markdowns. See, in our corpus ML we have markdowns, like you can see hashtag, machine learning fundamentals, and so on. We have this kind of data, right? That means this is like a markdown, and we can use markdown header text splitter to compute our stuff, right? Now to do that, we have something called header to split on. Header to split on. So here we have to mention based on which headers we will split our data. But in our scenario, we have data like this kind of data, right? So in such cases, we can use single slash means header 1, double slash mean header 2, triple slash or triple hashtag means header 3. So we are assuming that we have this kind of headers in our data, and it will do splitting based on that. So then I have called this markdown header text splitter, and inside the markdown header text splitter, I mentioned header to split on. So based on what headers it will do this splitting, it will do this splitting based on headers to split on, means this one. Okay, then strip headers equals to false, and then I am doing the chunking. Now before inspecting the chunking, I just want to show the chunking, so I'm just executing this code. So now this md chunks variable will contain my all chunks. So let's see those chunks. Md chunks. Okay, so you can see again I am getting a document kind of a structure because I'm using LangChain to do that. So I'm getting a document based structure. And now what I do, I just take the first one. Okay. So when I take the first one, I am getting a metadata and the page content. So I'm more interested on the page content. So I'm just clicking on page content. Now click on this, I'll get the page content. I just copy this part and just paste it here. If I do this one, word wrap, see, can you see it has only taken the first part, machine learning fundamentals. So it has only taken the first hashtag or the first header, and based on that it has done the splitting, right? Now if I try to do the same kind of a thing for this one, okay, so now see I am getting for supervised learning, which has two hashtags or header 2. So this is how we are getting the chunks. Okay, now if I really see the inspect chunks, we can get the information that it has created 8 chunks from my data, and out of that 283 characters are the average size, where 195 is the uh, minimum, and 414 characters is the maximum part. Okay, so this is the case. All right, so we talk about for a few more cases to get it better. Okay, so this is what we used, markdown header text editor. Okay, so I guess it is the same example. Yeah, it is the same example, so we can focus on this one. Yeah, where markdowns text editor. course, yes. So this is same code, so I just delete this part. Okay, okay, all right. So we have another part. So here you can see what we have. So we have added markdown header text splitter again under MD splitter. Then we splitted the text, correct? Then in the next part we did a hybrid chunking. Where what we did, we first did the header split and then we did the recursive size chunking. Okay, so how are we doing this kind of hybrid chunking kind of structure? So how we do it, first of all we have something called markdown header text splitter, where using this we are trying to do this splitting. Okay, and I was saying strip headers equals to true. So you can see what does it mean a strip header here. Strip split headers from the content of the chunk. So it will strip all the headers from the content of the chunk. Okay, it will not keep that headers. So if you really want to strip your headers, you can do this stripping like this. Okay. So then what we did, I did simple MD splitter strip. I've just called this. I have done this splitting on this data which contains inside header splits. Okay, after that what we did, we created one recursive character text splitter. Okay, recursive character text splitter. On top of that we have given 400 chunk size and chunk size overlap as 40, and we did this split documents. Okay, so if I really show that now, okay, by commenting this code. Okay, so there are many codes below that we will discuss, but for now let's not discuss everything in one shot. Hold on a second. Maybe my bus is losing it. Yes. Yeah, we can comment till this point. Yes. And I'm simply just executing this code. So what this code is doing, or what is the purpose of it? So see, hybrid search or hybrid, not hybrid search, sorry, hybrid chunking we are doing here. Why? Because first of all, we are doing this splitting based on the markdown. Once we are done with that markdown splitting, now your markdown may have a lot information, right? If your markdown has a lot information, in such cases we cannot really send that chunk into the LLM, because that chunk may also may also overlap the context window, right? May not fit into the context window. So that is why what we are doing, after doing this splitting based on the headers, then we are doing again recursive character text splitting, so that those chunks fits into the context window. Okay, that is the overall motto in our case. So you can see when I did that, and you can see that output here. So this is the hybrid one, where we are doing markdown header text splitting and the recursive size chunking, right? So we got 8 chunks, and out of that this is the information. Okay, so you can see I have this document like this, as well as I kept this kind of metadata. So now what I did, as I did this stripping of the headers, right, I have added those headers as a metadata into my chunk, so that it makes more sense. That is how we are doing that. Okay, so this is the another example of doing the chunking, document based chunking. So now what I do, I'll just show you another example of doing the chunking on some HTML page. So this is the HTML doc that we had. Okay, now let's say you got a HTML doc in your case and you want to do chunking on top of that. So how you can do that? Again, I know my HTML code, I can see my HTML code. So I have chosen some HTML headers like h1 page title, h2 section, h3 subsection, and then I did simple HTML header text splitter, and using that I have done the splitting. If I execute this code, you can see the output at the below. See, so I am getting the output HTML header splitter where I got 10 chunks. Okay, and see, it has added the metadata also, so that it makes more sense for the character for the chunks. Okay, so after that we have another example of the JSON. Okay, we have another example of the JSON. I'll show you that too. So what are you doing in the JSON? So in our case, we have a JSON data which has some configuration related information like open API, info, path, and all. Okay, we have this kind of JSON data. So if you really want to do splitting on JSON data, we can do that too. So for that, we have option like recursive JSON splitter. You can use recursive JSON splitter to chunk your JSON document also, and you can do split JSON, which will split the JSON. And if you want to, I mean, split JSON will have the chunk, okay. And when you call the create documents, then it will create the documents, like it will create the chunks first, and those chunks will be converted into LangChain documents. So I just wanted to show you that first. So let's print, or let's check the JSON chunk. Okay, let's first execute this code. Okay, so I have executed this code, and let's see the JSON chunks first. So when we do split JSON, what happens? If I come below and create a new file here and just quickly check. So can you see, when I did split JSON and the output is stored inside the JSON chunks. So this is how the chunks is look like when you are doing split JSON. But when we are doing this, when you are doing this create documents, on that time it is splitting and storing the chunks as a document format, which will be feed into the retriever or feed into the LLM whenever we will be doing that further, right? If I click on this doc, see, now you have the document based format. So when you call create document, it will create in this format, and this is the ideal format which we will feed into our LLM. Okay, so that is why we are focusing on this create document structure. So split JSON will help you to just create the chunks. And if you call create documents, it will create a document chunk structure inside LangChain, which you can easily feed into the LLM for the better retrieval, which we will discuss next after this chunking video. Okay, and this just has some information like how many you can get the information. See, right, how many JSON input, how many JSON chunks are created. It will just print this information. Okay, now the last thing inside document based chunking, that is this one, which I will be discussing now, that is the page level chunking. So let's say if you really want to do chunking based on page, so you may have a PDF document where you have multiple pages and you want to do page based chunking, you can do that too. Now further, what you need to do, simple, you just, again, right now we do not have any PDF to show you as example for multiple pages. So I'm just creating one simulation here. So when after this video, when we talk about retrieving or retrieval part, on that part we will use some real PDF where we will do the practical and we will get the idea more about this real PDF data. Because this scenario is all about chunking, that is why I am not using any document PDF to show you, because when we work on retrieval, on that time anyways we need to use some document, and on that part we can see the chunking and retrieval working together to generate a better response. Okay, so what happens when you want to do page level chunking, what you need to do, simple, just add the page content, whatever page content you have, and just add the metadata. In the metadata you can add the page, and if you may add the page in the metadata, so it will be easier for the model to see that if some information is already there inside page 2, then it does not go to other pages and look around for the answer. Instead, what it will do, it will just go to the page 2, page 1, page 4, whatever, and it can directly fetch you the answer. So this metadata will help LLM to find the proper chunks which will have the actual answers. Okay, so now to simulate the page, what I did, I created one list where I took the corpus AI and I took only till 800 characters for my corpus AI. Then from 800 till 1600 I kept for page 2. Again, this is the simulation. Again, from 1600 till the end I kept it for page 3. So these are my documents. So as I am sending them in a list format and I am calling the page level chunks, so what it will do, it will again run a loop. Okay, and it will assume that each part is in different page. So first data is in page 1, second data is in page 2, third data is in page 3. And because of that, what happens, that it will create a metadata where it will keep on adding the source as well as keep on adding the page number. Okay, if I execute this code, then we can get the answer. You can see, so in the page level chunking, so we have the data for page 1, we have the data for page 2, we have the data for page 3. So this is the way you can do page level chunking if you want to. Okay. So yeah. Okay. So now we talk about semantic chunking. So what is the semantic chunking? Again, this is discussed. So the core idea is embed every sentence, compute the cosine distance between consecutive sentences, and split where the semantic shift exceeds a threshold. Simple. Chunks group sentences that talk about the same topic. And there are multiple breakup points or breakpoints that we have in the semantic chunking that we can discuss. We can do percentile based semantic chunking, standard deviation based semantic chunking, interquartile based semantic chunking, gradient based semantic chunking. So when you work on percentile based semantic chunking, right? So the behavior is like split at top n% largest distance. So whatever percentile value we choose, based on that largest distance, it will split the document. The standard deviation. So based on the standard deviation formula, it will do the splitting, and based on this IQ or range and the gradient, it will do the splitting. Okay. So now we discuss about it. Now for this we need few things. First of all, we have to import. Sorry. First of all, we have to import from LangChain experimental import semantic chunker, right? Now, in for this project or for this kind of chunking techniques, we need some embedding models, because at the end we are going to calculate the cosine similarity, right? Now for that you need numbers. That means you need to convert them into embedding, then you need to calculate the cosine similarity. So there are multiple options that you can use. You can use OpenAI embeddings, you can use Gemini embeddings, you can use Olama embeddings, you can use Hugging Face embeddings. Okay. Now now right now I'm not using Hugging Face embeddings, because again, now to use Hugging Face embedding I need to install something, and it will install some document or some data in my laptop, and I don't want that. So that's why I'm using Olama embedding. Again, Olama embedding is also good, and I generally prefer, when it's about local implementation, I generally prefer Olama. Even if you see my laptop's thing, right, you can see, you might be seeing Olama is not running right now. If I just simply go and search Olama and click on this thing, okay, nothing will come up. But if I now come here, you will see Olama running now here. Okay, so now I will tell you how you can install Olama first. Then we will talk about further. Now to download Olama, nothing you need to do, just search Olama download. Okay, the simple search Olama download, and you will get a link. If you are using Windows, download it for Windows. If you are using something else, you can use something else. Okay, you need to download the Olama, and that's all only you need to do. Now to start Olama, you need to just call Olama, search Olama, and just click on it, and you can see in this place you can see which things are running, and if you are seeing that Olama is coming here, it means Olama is working. That's all it is you need to know. Okay, so now what I have mentioned already, that I am going to use Olama embeddings, right? Now Olama embeddings, and inside Olama embedding we have a model called nomic embed text, and this embedding model I am going to use to do the semantic chunking. Now the question is, how did I know that this is the embedding model? So for that you need to go simple, you need to go here, Olama embedding models, you need to search that. Okay, I'm just doing a simple search about it. Then click on, I think I will suggest, do not go to the other documents, go to the Olama blog or something like this. Go to this kind of documents. Okay, and in these cases you will always get the information about the model. Like I'm using this nomic embed text, there are models like mxb embed large, right? So you can use this kind of models. So now you can click on view model to view the model. Now if you really want to download, this model, what you need to do, you can copy this command. Okay, just copy it, open your terminal. Okay, open your terminal and just simply paste this command. Okay, if you paste this command, now what it will do, it will start pulling the nomic embed text in your laptop. It will be downloading this nomic embed text in your laptop, and then you can use it, okay, in your project. Now your question might be that you could have used Hugging Face also, because anyways you are downloading these things in your laptop. Yeah, it is true, I can do that, but Hugging Face install and brings multiple things in the system path. Now deleting those stuff again is a headache for me. Now removing something like Olama, this kind of models, whatever embedding model or whatever chat models I am going to pull in future, I just need to run one command to remove that from my laptop. I don't have to go to the system folder and find it out and then remove it, right? So that is why I kind of prefer using Olama. Okay, so for me it is showing like this because it is already there in my laptop, but in your case it may take some time to download it, and based on the model size it will take some time. So you can, if you want, you can install it like this. Okay, great. So let's go back to my case. So I am calling Olama embeddings here and I am calling the model. Now what I am doing is simple semantic chunking, chunker, and here I am passing the embedding model and I am doing the percentile based chunking, and I am saying breakpoint it will do when it will find 85 as a threshold point for percentile. It means split at top 15% semantic shift. If it sees at any top 15% semantic shift, it will do the splitting, and at start index equals to true. So, and then I am doing the create documents. So again, for standard deviation, for interquartile range, and for gradient, I have kept the example. Okay. So now what I do, I just simply comment this part for now. Okay, I just simply comment out this part because we do not need it for now. Okay, and we'll see the chunking. So I am executing this code directly so that we can see the output at the end. Okay, so now what is happening, you can see it is trying to use my Olama embedding model and it is trying to give me the answer. Now this thing may take some time to get executed. So it is executed for me. Okay, it is still executing for me, but in your case it may take some time to generate the output, because now it is this embedding model is in your laptop, and because of that it may take some time to um, execute. Again, it depends on your laptop power. That's it is. So now you can see when we used the percentile chunking, we got 5 chunk. Okay, when you use standard deviation, right, uh click on this. Okay, maybe it is taking some time or something. Hold on, I think my VS Code is hanging for some reason. uh okay, let's come below and let's try to click on this. I'll just execute it again just to be sure that it is working. Okay, we're not able to see the output for some reason. Okay, so as you can see, it is, I think because it's a big document, maybe that's just taking some time to show the answer. So let's do one by one. For some reason maybe my VS Code is stuck or something. So let's do one by one so that we can see it properly. Okay, so yeah, so when we did percentile based chunking, we got this kind of chunks. Okay, so you can see we got data like this and we got this many chunks, so we got 5 chunks, right? So let's see what is the chunk. Let's see, is it a semantically perfect chunk or not, right? So what I do, I just quickly pick up this variable because this variable contains the actual chunk, right? What I'm doing, simply I'm just listing it. Yeah, so now let's pick the first chunk and then pick the page content of it. So now if I execute this code, I'm getting the content. So let's see if this chunk is semantically meaningful or not, right? So yeah, so you can see, yeah, it makes a pretty good sense when it's about semantic chunking. You can see that it started with artificial intelligence, it kept it till this transformer architecture. So it has not splitted in between, it has splitted based on the end of any proper sentence. So, and if I see for the second chunk, right? Let's see again. See for this also, it has started with something like models like GPT-4 Claude 3 and all, and it has ended database at inference time. So it has started in a good point and it has ended in a good point. And each chunk is trying to say something about AI or trying to say something about the LLM models, right? So this is a very good chunking that is there, what I believe, right? So now let's do the another chunking again. I'm going to comment this section again because or else it will take some time for us to see the answer in the output. So now here I'm doing the standard deviation and the threshold is 1.25. So 1.25 sigma above means distance, right? So again, if I again do it and if I just copy it, I just paste it here again. So for this it got only two chunks, okay? So now if I execute this code, I may see the answer. And let's see. See, for this it got a bit bigger document. Again, this document is also a complete document, but the only problem is because we kept a very what do I say, very big value. Maybe that's why it is coming like this. So now choosing a standard deviation value actually matters a lot, as we understand. But I believe percentile one worked really well, or maybe you need to tune this standard deviation value to make it far better. Okay, but again, that you can do it if you want to, but for now let's not do it. Okay, great. Now the next one is interquartile range. So what interquartile range does, again same thing, same options. Okay, so if I execute this code, see we got two chunks again. Again, based on your interquartile range value, it will differ. So you need to change these values to get the better answers. Okay, again, this is the overhead for this technique. These threshold values play a very key role while choosing the semantic chunking technique. But again, I believe if you can choose a correct value or choose a very good tuned value, it can give you a pretty good quality chunks. Again, I'm not going to show the answer because it's same thing. And the last one is for gradient. Okay, so if you want, you can do gradient and you can pass the breakup threshold like 95. Okay, so if you give it like that, it will generate the perfect answer. Okay, so now below what we did, in below we have written a one custom code which will explain the semantic chunking. So again, I'll just explain the code to you. So what we are doing here, we have created a function called manual semantic chunker. We take the text, we are taking the embedding model, we are taking the threshold, then we are taking the minimum chunk sentence. Okay, so if we have sentences lesser than 2, right, length of sentence are lesser than 2, then we are returning the text directly as an answer. But if it is not, then we are working on it. So first what we are doing, we are trying to convert that sentence that we are sending. Okay, we are trying to send that sentence in the embedding model. So we got our vectors. Okay, so once we got our vectors, we are running the loop on the vectors, and then we are applying some dot product, and we are trying to calculate the cosine similarity. Okay, so and what we are doing, we are calculating the distance. So 1 minus similarity value will give us the distance. So once we get the distance, then we are creating the breakpoints. Now to create the breakpoints, what we are going to do, we are checking, we are first running the loop. Okay, because we got the distances, right? By running this loop, we got the distances, and what we are doing, we are running a loop here, we are running a list computation here, and if the distance is greater than the threshold that we have chosen, that means this part is approved for chunking. So we are only taking those as a breakpoints. So once we get our breakpoints, after that what we are doing, we are running the loop on top of the breakpoints, and then what we are doing, we are trying to split it based on the breakpoint value, and we are creating the chunks here, and at the end we are appending all the output. Okay, so this is how this whole thing is working. Again, this is the manual part of doing the whole chunking technique, but mostly you can use these available libraries which can do the same stuff, but just I wanted to show you how it looks like when we try to do the same thing manually. Okay, great. So now what are we going to do? We are going to go above and we are going to comment this part. We are going to complete the semantic chunking. So I believe guys you have understood how semantic chunking works in the practical part. Okay. So now I will explain you the methods that we discuss of semantic chunking in a visual manner so that we understand it better. Okay. So now you can see I I have taken few data S1, S2 till the S8. So S1, S2 and S3 contains the topics related to biology. S4, S5, S6 contains topics related to astronomy. S6 sorry S7 and S8 contains topics related to sensors. Okay. And we will discuss the different semantic chunking technique like percentile, standard deviation, interquartile range and gradient. Okay. So what we do, I just click on the next button. Okay. So you can see how percentile thing is working. Okay. So you have seen the code, right? So what we wanted to do, I have chosen breakpoint threshold amount 85, right? What does it mean? Split at top 15% of semantic shift by distance rank. How it works? First of all, what are we doing? We are simply calculating the distance between the S1 and S2, which is 0.12, S2 S3 0.18, S3 S4 0.91, S4 S5 0.14, S5 S6 0.2, S6 S7 0.55, S7 S8 0.16. Okay. Now what we are doing, we are sorting it. We are sorting all these distances. Okay, in a ascending order. Okay, so once we sort it and once we apply the 85th index, 85th percentile on top of it, we got the value as 5.1. We got the index as 5.1. Okay, so the 5.1 index threshold value becomes 0.59. After applying the formula, you will get the value of threshold of 0.59. So if something is more than 0.59, if distance is more than 0.59, that will mean that I need to chunk now. So that's why as per my data set, I got S3 and S4 distance 0.91. So where I need to implement the split. Okay, so you can see S1, S2, S3, S4 till this it's another chunk, S5, S6 is another chunk. Okay. Okay, so you can see, so when we implemented this one, right, so we are doing splitting based on this S1, S2, S3, S4. So our first split will happen after the S4. Okay, this side works. Next we have standard deviation chunk. Okay, how it happens? So again we have given these breakup point 1.25. So mean 0.32 and standard deviation 0.28. How we got it? By just calculating this from this data, we got mean 0.32, standard deviation 0.28, and then we apply this formula, that is the mean plus this the threshold value multiplied by the standard deviation. So by doing this formula, we get the threshold 0.67. Now if the distance is greater than the 0.67, so then we do the split. Okay, so this is how standard deviation is working. Okay, and this is the formula. Okay, then if I click on the IQR, interquartile range, how we are doing? Again, we are choosing the threshold amount 1.5 and we are sorting the distances between them. Then we are calculating the Q1, Q3, and then we are calculating the IQR. Now to calculate the threshold, what we are simply doing, Q3 plus 1.5 multiplied by IQR. Okay, okay, to fence. Okay, we just calculate this one. So by doing this, we got 0.73 as the threshold. Now if something is greater than 0.73, we are going to choose that as the split. Okay, next is gradient. If you see how we are doing it, again in the gradient we have chosen the threshold amount as 95. So what we are doing, we are first calculating the distance. Okay, then we are calculating the gradient. Okay, by doing this formula, the distance I plus 1 minus distance I. By calculating the gradients, we are getting the gradient value. Once we create the gradient values, we are sorting it. Okay, we are sorting it. Once we are sorting it, then we calculate the 95th percentile from that. Okay, and we get a threshold value like 0.76. Okay, and then we compare. If we find something that is crossing the 0.76, so on that time we do the split as per the visual. Okay, and then you can see we are getting chunks, right? So S1, S2, S3, S4, S5 will be the one chunk, and S6, S7, S8 will be another chunk. Okay, so this is the gradient chunking that we are choosing while doing the semantic chunking. Okay, now if we really want to compare, right, we can see how it is coming up. So this is the output that we are trying to showcase. So this is the visual understanding of different types of semantic chunking that we were implementing in our practical. Now we talk about LLM based chunking. So what is the core idea? So what we do here, we feed text to an LLM and ask it identify semantically meaningful split points. The LLM understands the narrative structure, topic translations, and theoretical boundaries that heuristic splitters cannot detect. So that is why we are mostly focusing on this LLM based chunking. So there are different variants that we will be exploring today. First one is boundary detection, where LLM marks split position in raw text. Then structure extraction. LLM returns JSON of sections. Then contextual enrichment. LLM adds summary or context header to each chunk. So that's how we are going to focus on LLM based chunking. These are the pros and cons mentioned. I'm not going to read it out again because already discussed in the previous section. So for this, what we are going to do, we're going to import few things. So you can see I've imported Olama, Chat Olama, because at the end I'm going to use Olama only. That's why I'm using Chat Olama. Then I'm not going to use these libraries, but just I've kept it. I'll be using Pydantic as base model and field. I'll be using this to do that. Okay. Now what I'm doing here again, same imports I'm doing. I'm calling LLM. Okay, I'm calling LLM, and from that I'm calling Chat Olama. So I have pulled Llama 3.18 billion model. So again, the way we pulled embedding model, the same way I have pulled chat models now. Llama 3.18 billion models. Okay, and it has the temperature 0 that I have chosen. Okay, the next question is, how are we going to implement the boundary based thing, right? Now again, as I said, we are going to fit our whole thing into the LLM, which is like the way we are going to do it. Now this is the boundary prompt. What is the boundary prompt here? So we have provided one chat prompt template, where we have provided one template, like you are an expert document analyst, identify the natural topic translation points in the text below, where a new distinct subject begins. For each transition, return the exact first few words of the new section return, only a valid JSON array of string, no boundary, no explanations. Okay. So for this I have created one Python function where I have simply created this class, okay, boundary output, and this is what it will return, the boundaries, and it will contain the list of section start phrases indicating topic shifts, and I have added this as a chain boundary prompt and the LLM with structured output. Okay, now through the response I am going to invoke the chain, and then what I do, I am going to pick the output using the boundary key, and then what I'm going to do, once I get the boundaries, after that I am going to run a loop through the boundaries, and I am going to find the position. Now because I got the boundaries, right, I got those key phrases. So what I do now, I simply do tx.find to understand or to find the position or the index of the specific phrase, and after that I am going to, if the position is greater than 0, I am going to append that inside the split position. So I am going to append all the indexes of those sections, okay, inside the document. So I am going to add all of them inside this split position, and then I am going to sort them. So once I have sorted them, okay, then what I do, I run a loop. Okay, I run a loop. I will try to get the end of the, I mean, once I run a loop, right, I need to create the chunk. Now to create the chunk, what I am doing in this line, you can see what I am doing here. I am checking if I plus 1, okay, if I plus 1 is lesser than the length of split positions. If this is true, then it will do split positions I plus 1. So if this one will be true, right, then what it will do, it will take the split position I plus 1, okay, and this will give the end value, that means end of the chunk, right? Then what I do, I'll just simply use slicing to get the chunk. So start index we already have, and we get the end index by doing this one, and then what we do, we just take the chunk. So if we get the chunk, then what we are doing, we are appending inside this list as a LangChain document. I have already explained to you how LangChain document works. So by doing this way, we can easily add inside our chunk. So this is the part that we are going to implement now. So this is the boundary prompt. Okay. So if I comment out the below code and try to execute the further things. So guys, this part will be a bit bigger part. Okay. This LLM based chunking, it has a lot of things that we can do. Okay. It might be a bit bigger part. Okay. So once I execute this code, so you'll see it may take some time, because again it is hitting my LLM model which is there inside my laptop, right? So now based on your laptop configuration, laptop RAM memory, it will take some time. So if it takes some time, we have to wait for it. But if you have OpenAI API key accesses, or if you have any Grok API key accesses, we can do that with. But I'm just using Olama because I like Olama, that's why. I could have used Grok also, but I'm not using Grok here, I'm using Chat Olama to do it. Okay. Okay, so you can see it has executed that, and it got some boundaries like in healthcare, the finance sector relies in heavily on AI fraud detection. So it is getting these kind of boundaries. So now based on that, it got three chunks. So these are the three chunks that it got. Okay, so this is the first part. Now again, I am going to comment out this first section, because or else we may not be able to see the output in my system. Okay, all right. So this is the second part where we are going to do based on this one, based on structured extractions. Okay. So for structured extraction, what we are doing, we have created a prompt template here. Okay. That is the chat prompt template. So divide the following text into distinct the distinct thematic sections. For each section, provide title, content, keywords, written only a valid JSON and all, and we get the title, content and keywords. Now for that I have created one section here. So we have this section, and as we are going to save all of them as chunks, right? So these things will be stored as chunk, right? These things will be stored as chunk, and because of that I am creating one sections. So those sections will contain the chunks. So these chunks will be these kind of informations. Okay. Once we have this section, and now sections will contain the chunks, and these chunks will be the section here. Okay. So now this is the function. Again, I have just kept a print statement for my understanding, and here I am adding the again the section prompt and the structured output. Okay, and this will store the chunk. So if I execute this code, so I should get the output again, and I'm getting a name error. List is not defined. So this is an import problem, guys. So now to fix the import problem, I need to call out like this from typing import list. Okay, I need to call this. So now this code should work actually. So now again it is going to hit to my model. So now it may take some time to hit it and get the output. So let's wait for that. Okay, so we got the answer again now. So now we got 7 chunks. Okay, and you can see this is the chunk example of the one chunk. Okay, so this is how we are getting the chunk. Okay, now this part is also done, so I will just comment it out this section and we'll focus on the further sections. Okay, so then the next section is contextual enrichment that we'll be focusing on. And contextual enrichment code is a bit bigger one, so I just try to show it to you. Okay, so what we're doing here, first of all, again we have the prompt here. We are saying you are a given document and one chunk extracted from it. Write a short 1 to 2 sentence context prefix that situates this chunk within the full document. So the prefix will be prepended to the chunk before embedding and be conscious and factual. So what it will do, it will just add one enrichment, like contextual enrichment in a short sentence. Okay, so that's what I'm doing here. I'm adding that, okay, with my LLM. Okay, so what I'm doing here, I'm trying to, for the example, I'm trying to keep only till 1500 abbreviation. Then what I'm doing, I'm running a loop. I'm running a loop and I'm trying to invoke. Okay, I'm running a loop and I'm running a loop for the maximum chunks. Right now I've chosen chunk size 5. So for maximum chunks, what I am doing, I am trying to run a loop and then I am trying to execute the chain with these document abbreviations. Okay, and then whatever abbreviations we are getting, that's what I am adding in the as a document in the enriched list. Okay, so enriched list will contain the actually the enriched context document. As a LangChain document it will be stored, and the chunk details will be stored as a metadata for the specific enrichment. So this way what will happen, it will get the context, the main contextual enrichment context in the page content, and it will get the chunk metadata in the metadata section. So this way it will be easier for the LLM to find the answer whenever it will be hitting through the retrieval. Okay, so this is what it will return, the enriched chunk. After that I am getting on base chunks, because for the contextual enrichment you will already need one chunks. Okay, you first need to have a base chunk which will be enriched by this method. Okay, so that is why what we are doing, we are simply creating one base chunk using the recursive pattern text splitter. Then we are sending the base chunks into the enrichment one chunk, and then we are getting the answer. If I execute this query now, what it will do, it will get the base chunk. So now contextually enriched chunks we will get. So we are getting almost 3 chunks, and you can see these chunks. Okay, so this is the way of doing the LLM based chunking. So now we focus on the agentic chunking. So what is the agentic chunking altogether? So an LLM agent decides chunking strategy dynamically per document. So what it will happen here? Here agent will choose which chunking method I need to use. Nothing else apart from this. Okay, it will choose which technique I need to use. That's what agentic chunking will be doing. Okay, so let's see the code for that. Again I'm using this some purpose, and sorry, I'm using some parser here, and then I am calling the proposition prompt. What this proposition prompt will do, this, you are an expert and extracting atomic propositions from the text. So this will extract the proposition from the text. A proposition is a single complete self-contained factual statement that can be understood without reading the surrounding text. Replace all pronouns with the actual entities they refer to. Preserve all numbers, dates, percentage and proper noun exactly. Contains only one distinct claim per statement. So this is the proposition prompt, and I just continue the proposal. I will contain all the proportions in a list of strings. Okay. Then I'm creating the chain. Then I'm hitting the chain. Okay. You can see. Then I'm hitting the chain. So I'll get some answer. Okay. So this is what I'm doing here. So the same code I have explained below. Okay. This is what I was testing on that time. Okay. So that is why I just kept that code as it is. But when I execute, and I'll show you more how it will happen next. Okay. So I just, for now, I just stop it. I just don't want to execute it, because next again we have the same code written already for that. Okay. So I think I just can stop this. Yes. Okay. So you can see I got some proposition output, but again we will see in the next section. But yeah, so I've done some imports. Then what I did, I have created the proposition prompt, same prompt. Then what I'm calling in the function, I'm calling the text, I'm passing the LLM. I'm telling the para chunk size. So I'm telling the chunk size should be 800 and verbose equals to true. So what I'm doing here, first of all, I'm doing recursive character text splitter to get the splits, right? Once I have that, once I have the paragraphs, I'm going to send that inside the chain that I'm creating. Okay, this is the chain. So once I have this paragraph, I run a loop for each paragraph or for each chunk that we get from recursive character text splitter. We are sending that inside the chain. Okay, and we get the response, and we pick the propositions, and after that we run a loop on top of the proposition, and then we are returning one document, LangChain document, which will contain the proposition output as well as the metadata. Okay, so once we have the metadata ready, once you have the metadata ready, we get those chunks inside the prop chunks. Okay, so prop chunks will contain the chunk. Okay, so if I really show you that also, before showing you anything else, I just simply come below and just try to comment out all the parts. Yeah, so now if I execute this code, we get one propositional chunking. Okay, so you can see I got almost 10 chunks. Okay, and let's see the chunk. Okay, so let's see the chunk. So let's try to see the chunk here. Execute this code. See, I got this chunk. Okay, so page content is containing the propositions. You can see the propositions containing here. Okay, but guys, see, this is not the ending of one technique. Okay, so the agentic chunking that we are doing, right, it is going through some steps. So proposition chunking is the first step of it. It is not done yet. We are doing it further. Okay, so once we have this proposition prop chunks, right, then we are going to do quality scoring. Okay, so what is the quality scoring here? So we have one quality scoring here. What do we do? Again, we are trying to rate the propositions. Now once we get the proposition chunks, we are trying to rate the proposition, like 5 4 3 2 1 karke we just rate it. Okay, so we are trying to filter now. So once we get all the propositions, right, we are trying to filter it. Okay, we are trying to filter all the good propositions, and I have kept a minimum score 3. So if any proposition gets score lesser than 3, those propositions will not be taken further. Okay, that's what we are doing. Yeah. Again, I'm going to uncomment the next code too, because anyway this code is pretty easy to understand now. So I just comment out, uncomment all the section now. Okay, so this way you get all the filtered propositions. After that, we are doing the strategy selector prompt. So this is the prompt which will actually tell me which one to pick. So I'm giving it 4 options: fixed size, recursive, semantic, or markdown error. Okay, and same already marked in the strategy map. So this is one dictionary format where we have already mentioned that which technique it has to pick. If it picks A, then it will do this kind of chunking. If it picks B, it will do this kind of chunking. If it picks C, then it will do semantic chunking. If it picks D, it will do this markdown header chunking, right? So now adaptive agentic chunker will do the actual step. So what we are doing here, we are sending the strategy selector prompt with the LLM structure output, and once it get the strategy and get the reason, right? So we are not only fetching the strategy, we are fetching the reason also. Because tomorrow, if you really want to know that why it has chosen some strategy, we can get it through the reason. Okay. So after that, we are doing what we are doing. We are simply getting the chunk. Okay. We are choosing the we are storing this as a metadata. Okay. We are storing all the information as a metadata. Then what we did, we simply ran a loop for sample text. So what, yeah. So for sample text and labeling corpus AI, so we are picking two data. We are picking corpus AI as a plain article and corpus ML as a markdown doc. So if I execute this code, so and if I call this one, right, we will get the chunks, agent chunks. Okay. If I try to print agent chunks, right, we can print it. If I try to print the agent chunk, yeah, we are trying to print the agent chunk, and I will try to print some separator so that we understand that it is working. Okay. I will try to print it so that it will show that chunking is working. I just quickly execute this code, and now you will see all steps happening. Okay, first proposition chunking will happen, then strategic sorry, not strategy, then quality filtering will happen. After that, strategic selector will happen. So strategic selector will be picking up the all the things, and at the end we should get our output. So we are sending the corpus A, corpus ML as our data, and let's see what all chunkings we are getting after the all step. Okay. Yeah. So let's see, if I click on text data, we get the output. See, so you get this kind of chunks. Okay. Yeah. So what we got, we got like this 10 chunks produced. Okay. So this is the chunk. So if I try to do the word wrap, I'll get the C. So this is the chunk we got a document format. See, this is the final chunk that we got for the corpus CI and corpus ML document. See the further chunk we got. So this is the example of agentic chunking. So agentic chunking has a lot many steps that you have followed that you need to focus on. Okay. All right. All right. So let's talk about the next chunking, that is hierarchical chunking.
So
So
now
what?
we talk about the hierarchical chunking. So the core idea of hierarchical chunking is building a multi-level tree. So that's all about hierarchical chunking. Okay, and we call it as a raptor also. There is a paper called raptor, which means recursive abstractive processing for tree organized retrieval architecture. So this is the raptor architecture. So here we have few parts like leaves, intermediate nodes, root. So leaves will be the fine grained raw chunks. So once you split your data, right, then that chunk you get, this is the leaves, which is the level 0. Then intermediate nodes, LLM summarizes of cluster of leaves. So what it will do, it summarizes each chunk. Okay, so this can be one level up, level 1 or level 2, right? And at the end we have a root node, where which is a single top level summary of the whole document. So we have some levels here: leaves, intermediate nodes, and root. So through this way, we try to create one hierarchical chunking. So you can see the example mentioned here. In the level 0, you have leaf nodes like leaf 1, leaf 2, leaf 3, leaf 4. Okay, these leaf nodes are nothing but the chunk that we do at the very first time. Again, in the implementation I will show you now, but just for your idea. So level 0 will be the leaves, the raw chunks that we get. After that, what we do, we go one level up. So what we do, we try to create clusters. We use k-means clustering algorithm to cluster our leaves. Okay, like why are we clustering it? Now few chunks or few leaves may contain some specific information, right? So that's how we clustering them. So let's say I got one cluster for leaf 1, leaf 2, I got another cluster for leaf 3, leaf 4. So what I do now, I'll take this cluster, cluster A, which contains the information of leaf 1 and leaf 2. We will be summarizing the cluster A. Likewise, when you get the cluster B, which contains the information of leaf 3 and leaf 4, we are going to summarize that thing. So this will be the level 1. So now when we go to level 2, which is the root summary in our scenario, we are going to summarize this cluster A information, cluster B information, and then we store that in the root. So right now what will happen, if your LLM, whenever it will hit for the retrieval, on that time it may need some answers from leaf 0, level 0. That means answer might be there in the leaf node. If answers are not properly given in the leaf node, what it will do, it will go to the level 1, where it will get the cluster wise summaries, which will be more precise for LLM to understand that okay, I may get information from this level or from this part. And at the end it will go to the root summary where the whole document summary is given. So if sometimes it has to answer that kind of questions where it just needs the whole document summary, it can directly go to the level 2 and it can generate the answer. So I am giving LLM multiple options, multiple places to go for and generate a better response. That's how we do that. And we generally use it when we have very long document. We have multi-hop Q&A, on such cases we use it. So for this again I am going to show the implementation. Again I will not explain you the code exactly line by line, but I will definitely give you the idea, so that tomorrow if you see this code you will mostly understand. So I am using recursive character text splitter here, I am using chat prompt template here, I am using Olama embedding here, I am using Grok as a chat model. As I said, I will be using clustering algorithm. So I will be using k-means clustering, then numpy, time, then data class, and then optional. So here what I am doing, here I am calling the chat Grok. I am using Llama 3.1 8 billion model. Okay. Now I am create a data structure for 3 nodes. So whatever nodes we will be creating, right, those node will have this kind of structure only. Okay, which will have text, level, then the embedding, then the children, okay, then the metadata. Okay, and this node will have a method called toDocument, which will convert this data into a line chain document. Okay, that's what it will do. Then I have another called summary prompt that I discuss later. Okay, and there's something called cluster and summarize, that also I'll discuss later. Let's come back to the main part. Build raptor tree. So this function will be building the raptor tree, okay, the hierarchical structure, and I'll be discussing that part one by one. So the build raptor tree takes few parameters. First of all, the text, the actual document. So here I am passing the corpus CI and corpus ML, right? Those two documents I am passing them with some new paragraph separator. Okay, in the embedding section I am providing the Olam embedding model. In the LLM section I am providing the Grok LLM. Leaf chunk size I have mentioned 500, and maximum labels will be 2. That means 0 1 2, this many labels will be there. 0 will be the leaf 1 will be the intermediate node, and 2 will be the root node. Okay, so when I call this build raptor tree, so what it is happening, you see, first we are doing recursive character text splitter. So this is we are doing for the level 0, right? So that's how we are doing a simple chunking. We are doing a simple chunking. Okay, so once we are doing the simple chunking, we are storing that information in the leaf text. Okay, after that what we are doing, we are running a loop on this leaf text, and I am creating a tree node. So whatever chunks I got, right, I have converted those chunks into the tree node structure. Nothing, I just ran a loop and I just set them as a tree node, where I took the text document as a T, label I mentioned 0, I have a metadata like chunks index I, and that's all. Okay, I'm not I'm not filling everything, guys. See, in the tree node I have multiple structures like the embed, if you see, embedding and all, right, but I'm not filling the embeddings for now. I don't have the embedding of my chunk right now, so that's why I'm only filling the text part, label part, and the metadata part. Okay, so once I have that, I have just stored in a label like 0 means leaf node. Okay, and then I'm saying current nodes equals to leaf nodes. Okay, so then I'm running a loop. As I've already mentioned, right, I am choosing max 2 levels, 0 1 2, right? So now here what I'm doing, I'm running a loop for 1 comma maximum levels plus 1, because maximum levels will be 2, 2 plus 1 will be 3, and when you run a range 1 comma 3, we get 1 and 2, because right now we want only 2 levels, sorry, total 3 levels, 0 1 2, and we have already the 0 level. Right now we are on the 0 level, so we have to start from the 1 level, right? So now we are in the 1 level, and when current nodes are less than equals to 2, we will stop the process. Why? Because if you have only 2 chunks, right, then it does not make sense of doing these many steps. That's why I kept it like this. When you have more than 2 nodes, then it makes sense going through this hierarchical chunking. So what we are doing, we are creating the one parent node, which will be the one node level up. Okay. So when I click on this parent node, in the parent nodes I am calling this method called cluster and summarize. It takes the current node. Current node means the current leaf nodes. Okay. Then the embedding model, and then the LLM and the level, which is one right now. In a first loop, it will be one. If I go to this cluster and summarize, see, this is the function. So what this function is doing, simple. It's for extracting the text from the nodes, then it is converting them into embeddings. Then this loop, what it is doing, you know, right guys, these nodes are nothing but the tree node data class that we just mentioned, right? It has one key called embedding. So what I'm doing, simple, I'm just creating the embedding and I'm just updating that embedding. So now in the tree node, I am updating the chunks embedding also. Okay. And after that, I am simply choosing the n cluster, how many cluster I want. And after that, what I am doing, I am simply running the k-means clustering. And by doing the k-means clustering, I will get the labels. Okay. And I am choosing two clusters, or k value equals to 2. So it will get 2 clusters only for now. Then what I am doing, I am running this chain, which has the summary prompt. This prompt has the summarization information and the LLM. So what will happen, it will take the each leaf node, right, and it will take the cluster of it. That means one cluster will have 2 leaf node information, and another cluster will have 2 leaf node information, and those 2 leaf node information will be summarized using this chain invoke method, and then we are going to save that inside the output of this node, parent tree node. As I said, all node will follow this tree node data class only. That's why I am returning the output as a tree node. Okay. So at the end, we get the level 1 output structure. So once you get the level 1 output structure, we again run this loop. Okay. For level 2, it will again process the whole thing, and it will again return as the final node. Okay. And that's how we get the output. And there is another method called flatten tree. What is flatten tree is doing? Simple. After all the processes, what we are doing, we are running a loop based on each level, and we are fetching all the chunks, okay, or all the documents in this docs list, so that we can see what all chunks are getting created, right? So that's all we are doing in this case. And if I execute this code, we'll get more information. So again, you can see it is now executing. I kept one time dot sleep 5 here. If you see in this code, if I show time dot sleep 5 here, um, if I show you that, yeah, here. Why? Because sometimes if I keep on hitting the grokna, it may throw some timeout error, and that is why I kept it like this. Okay, so that it doesn't throw any timeout error. So you can see it is executing right now. See, you can see the printing level 0, then level 1, then level 2. Okay, see, we got the answer. If I just click on this text editor, I can show you the output. See, laptop preserve level 0 got 70 leaf nodes, the level 1 got 4 nodes, the level 2 got 2 nodes. Okay, so first level contains the basic chunk or the base chunks. This contains the summarization of those clusters, and this contains the root structure. Okay, so this is the thing that you wanted to see in hierarchical chunking. So now we talk about late chunking, and for late chunking I have kept a separate notebook where I'll explain you the late chunking. Okay, now we talk about late chunking. So I will explain you the late chunking through the implementation, as well as I have prepared one visual where I'll explain you the steps of late chunking. Let me just explain you late chunking through these steps. So we first see the problem. We build a naive rack baseline and watch it fail on a real query. Then we are going to build the late chunking from scratch using the Hugging Face transformer library, and this is the ground truth implementation. You will see every step. And then we use the Gina API path, which will do the same thing but in just 3 lines of code. And then we compare the embedding side by side, which cosine similarity plot. Okay, all right. So now what I am doing, so first before starting anything, I need to do some basic imports,
So I have moved
which I'm
myself in Google Colab because my laptop local system is not able to support because of some reasons, maybe that's why I'm kind of moved to Google Colab. And you need to execute this command. You will execute anything in the notebook. Okay, then you can execute this command, and this is the document that I have already showed to you, right? So this code has already loaded all the models, right? So now what I do, I'll just quickly load this cosine function, and for that I need to execute this line also. Yeah. So this is the cosine function which will actually generate the cosine similarity between these 1D vectors or 1D arrays. Okay. And you can see, when you can see the similarity between the query and the chunks, okay, mentioned here. So the first chunk has the similarity of 85%. Second chunk has the similarity of 0.77%, and chunk 3 has the similarity of 0.71. Okay, but the actual answer actually resides in chunk 2, not in chunk 1, right? So you can clearly see how the naive chunking is failing here, because it is getting the most similarity with the first chunk, but actual answer is there in the second chunk. And why it is happening? Because in the first chunk I have discussed about Berlin, but in the second chunk, I discussed about 3.85 million, which is the actual, question that I wanted to answer, right? But as it has the mention, it's more than, which is not, um, semantically properly mentioned here, right? So it's means the Berlin, but here in this English text, Berlin is not mentioned anywhere. And that is why um, it is getting less similarity. Now what I do, we are going to do the late chunking. Okay, so again we are going to do late chunking from scratch, and then we will see how we can do the same thing using GNIPA. Okay, again these are the three steps how it will happen. Again through the visual also I'll explain it to you, but let's do it first through the coding steps. So first what we do, we first tokenize the entire document as one sequence. So you can see this is the function which will be doing all the tokenizing steps. Then we are going to run a single forward pass to get the token level embedding, and every token vector now encodes the whole document via self attention. So self attention will help you to understand the each token dependencies or each token meaning, right? So when we do the self attention, right, on that time, this it's, you can see, right, this it's will be able to connect with Berlin, because self-attention, what it will do, it will try to connect with every possible tokens that I have in my data set, right? So it will try to see are they related or not through the self-attention. So if I do the self-attention like that, right? So then it will get the value that okay, this it's means the Berlin that we are trying to mention, right? So that's how we are doing this step. And after that, we are going to find the token span for each chunk. And then we do the mean pool the token vectors in the span. Okay, so let's see that. First, this is the function that is going to tokenize the sentence one by one. Okay, and this is the function which will return the embedding per sentence using late chunking. So you can see we are first tokenize the whole document as one sequence. Then we are doing a single forward pass. Then we are doing building spans and mean pool per sentence. Okay, as we are doing that, and if I execute this code, so yeah, this is token spans per sentence, and this is the late chunk embedding shape. Okay, we are getting late chunk embedding shape. Okay, so now what we are doing, let's execute this code, and now let's see. So once we get this late chunking values, and now if I really want to see the cosine similarity now can you see chunk 2 got 89% of the cosine similarity. Why? Because when we apply the self addition, it has understood the meaning of the its that's there inside the second chunk because of the self addition, and that's why we got the 89%, which is the highest uh, similarity that we are getting. Now your LLM can answer in a better way, right? So if I really show you graphically side by side that how it will looks like, so this is the answer. You can see when we did the naive similarity, naive chunking, based on naive chunking, we did the naive similarity, we got 0.8587, which is almost same after the late chunking if you say. But when we did for chunk 2, for naive chunking we got 0.77 similarity, but for this we got 0.89 similarity, which is the pretty good output. Even for chunk 3 also we got a pretty good output, we got improvement here. So you are getting 0.8624. So can you see by applying late chunking now, it's not only improving your actual chunk output, it's actually improving other chunks also, which is actually a good thing, right? So this is how it works. So now, but the easier way, like instead of writing this many codes, the easier way of doing it using GNIPA. So How you can get the Gina API key? Just search Gina API key. You have to just Google Gina API key like this. So you find Gina API key and you'll get the Gina API key. Yeah, Gina AI. So if you go to the APIs, you'll get the API keys. So if I go to the API, see here I can get the API keys. Okay. So this way you can get the Gina API key. So Gina AI is one company who is actually maintaining this late chunking technique. So if you want, you can come here. You can copy the chunking, copy the API key from here, and you can use it. Okay. So I have already pasted it here. Already pasted the Gina API key here. You can see the Gina API key here. So what I do, I quickly execute this code. So here what I'm doing, I'm simply calling this API. This I'm requesting through this request library and I'm hitting this embedding. Okay. And after that, what I'm doing, I'm saying late chunking equals to late chunking. So in the JSON, I'm passing the late chunking, which is by default false mentioned here. Okay. So what I'm doing here, I'm simply saying Gina embed a late chunking equals to true. So when I'm saying late chunking equals to true, on that time now it will do the chunking based on okay, skipping API section says Gene API dot env to run this. Okay. So by any chance it is not able to find out the Gene API key. Let me hard code it for now. I have to edit this code for some reason for now, but for now I'm not editing this code. What I'm doing, I'm hard coding the Gene API key for now. I know this is Google Colab maybe, but that's why I am getting some issues. I'll fix it later. For now, what I'm doing, I'm simply just pasting the Gene API key and executing this code. Okay. So now it will get this answer now. See, now can you see? Now when we are using Gina embedding, right? See, for the naive we got 0.6178, 0.4828, 0.3173. But when we do the late chunking using Gina API key, we got 0.7901, which is the late chunking similarity. So you can see late chunking similarity is giving us a best answer instead of naive chunking, right? So so if you want to use Gina API key, you can use Gina API key also, and you don't have to override with writing any code for late chunking, right? You just have to say late chunking equals to true, and it will do your job. Okay, right? And if I visually show you the differences here, so this is one visualization that I have prepared, right? So you can see if I just quickly do zoom out and show you. See, when you ask the question, what is the population of Berlin? So you got chunk one like this and that, where this blur one is late chunking and this bright one is late chunking. So for chunk one, we are getting almost same similarities. But when we are using chunk two, in chunk two we got lesser similarity for chunk two. But when we did for late chunking, we got a pretty better similarity. And this is the answer you can see, right? Answer leaves here. Answer leaves on this bar. And chunk 3 also was a bit lower, but when you use late chunking, we got a better answer, right? We got a better answer. So yeah. So now what I do, I'll just show you the how late chunking works in a visual manner so that you understand it better. If I really show you how late chunking happens step by step through this visual, you'll get it in a better manner. So in our example, you can see our example document has 3 sentences. Crucially, the word Berlin appears only once. In sentence 1, sentence 2 and sentence 3 refer back to it as its and the city. So Berlin is Germany's capital. Its population exceeds 3.8 million. The city is also a state. Okay. So the query is, what is the population of Berlin? So the answer sits in sentence 2. You guys can see it, right? This is here. But sentence 2 never says Berlin. It says its. So naive chunker embeds each sentence in isolation and loses this connection. Late chunking fix it. So how late chunking will work step by step? Let me click on this next. So what we are doing in the step 1, we are tokenize the whole document as a single sequence. Every word becomes one or more tokens. Special markers like CLS and ACP bookend the sequence. So notice the 3 sentences flow into one unbroken stream of tokens. So you can see CLS is here, then Berlin is apostrophe is capital and everything divided into tokens. So the sentence boundaries are still known. We track token offsets, but the model is about to see this one long input, not 3 separate inputs. Okay. So model will see all this long input, not the separate inputs, right? Now next. So next what is happening? So in step 2 we are doing one forward pass through the embedding model. Every token is converted into a vector, here shown as 6 colored cells per token. Real models uses 768 or 1024 dimension. Self attention runs across the whole sequence at once. So each token's vector is shaped by every token, including tokens in other sequences. So you can see this is colored in a separate token, this is colored in a separate manner, and this is colored in separate manner, right? So you can see this is the key moment. The vector token its in sentence 2 has now attended the token Berlin in sentence 1. Okay, this is what is happening, guys. So the Berlin in sentence 1 and the its in sentence 2. Now because of the self attention, what is happening? Because of the self attention, now this its is attending Berlin. So now because of the self attention, it is able to understand that okay, this its means the Berlin that we are talking about. Okay, and this is how it's happening. See, now what we are doing, we are group the tokens by sentence span and then mean. So first of all, we grouped all the tokens. Okay, so this is the first token. So I mean first sentence, and this is second sentence, this is third sentence. So we grouped all those tokens, sentence one's token, we have grouped them, and after that we did a mean pool. So we calculate the mean of all of it, and we got the chunk vector like this. For this is the sentence 1 chunk vector after the mean pooling. This is the sentence 2 chunk vector after the mean pooling. This is the sentence 3 chunk vector after the mean pooling. Now the chunk vector for sentence 2 now carries the Berlin context baked in, even though the word Berlin never appeared in the span. That's the whole trick. So now this vector, this sentence 2 vector has its. It has still its, but now it has the context that okay, this its means the Berlin that we are trying to understand, right? And now, if you see, if I ask this question, what is the population of Berlin? We are getting the highest similarity for the sentence 2, right? So this is the visualization I wanted to explain, because if you see the visualization, you will get it in far better manner. That's how we are doing that today.